So thank you very much. So I think today I will just make it relatively informal. So for a company like OriGene come to a pathology conference and telling everybody that, okay, we're going to launch the most specific antibody in the pathology market, you probably ask me, who are you to tell me this is an old industry? So, is it truly our position to claim that? And I hope I can convince you one way or another that we have some unique technologies that we can make a more specific antibody. Okay, so that if the take-home message is that I think I have done my job, okay. And I always thought, by going to this field, the genome is our body's, I call it the operating system of our body. So personally, I'm a big believer that our genomic information really is eventually going to transform how we look at diseases or disease management. And OriGene is a company kind of started with the thesis that the genome, the decoding of genome will create a huge wave of technology innovation. And these innovations can eventually be applied to every aspect of human healthcare. And today we would like to share with you some of the technology we're developing around the antibody validation area. So the genomic field, so we now know since year 2001, we finally decoded our entire genome. And we know that in our whole human body now have about 20,000 protein coding genetic units. Like say insulin is one genetic unit, or BRCA1 is one genetic unit. So we have about 20,000. And this is really the operating system. The protein is what I call it the application software of our body. So how do we change the paradigm? And after the genome is decoded, how do we take the whole genome to help develop products to better manage diseases? That's really what OriGene is all about. And we're very much focused on developing the toolbox for this field. And tools are very important. So I give a few examples, PCR machines. I think this is a peptide synthesizer, DNA sequencing machine, patch clamping. So many of the innovation in the biology is driven by the innovation of toolbox. So if you look at the genome project, the first genome cost $1 billion to decode. Right now, $2,000, so you can have your sequence genome decoded, personal genome. So we have come a long way in genomic technology innovation. And OriGene is continue to push the frontier of this field. So OriGene's focus, a little bit brief introduction, is we started in 1996. We have been around for now 16 years. Time goes fast. I thought it was yesterday. We have about 400 employees. Our headquarters is in Rockville, which is the headquarters, where the entire human genome was decoded. We have actually a subsidiary in Seattle called Blue Herring, which we actually do synthetic biologies. We actually synthesize the backbone for Craig Venter. The first synthetic live organism is actually done by us. And we have a quite large organization in China. We do monoclonal antibody production in Beijing, Wuxi, and we also recently merged with a pathology company in China called ZS Bio. They are actually the oldest pathology company in China. It's been there for 20 years. And we distribute a lot of the global reagents for the pathologists in China. So actually, OriGene's long-term goal is to develop assays for every single protein in the human proteome. So if you think about a company like Illumina, the world, they have Affymetrix, the world, they have revolutionized how we detect the DNA and RNA. But today, if I challenge you and say, I give you a tube of my serum and say, go help me detect 10,000 protein in my serum, what is the technology you're going to use? So the technology is not quite there yet when it comes to detect the proteome. So we actually are pushing this in two frontiers. One is we are actually developing mass spec standard, for every single human protein. This is a collaboration we did with Leroy Hood at ISB in Seattle. It's funded by the government of Luxembourg. So we just contributed almost 5,000 purified human protein to Lee, and they're generating mass spec standard on every single one of them. So that's one direction we're going. The another direction is to make perfect antibody for every single human protein. So, and today, since this is a pathology conference, we really want to share with you our effort in the pathology side. So our unique capacity is, one is we dedicated 16 years to physically isolate an open reading frame clone for every single human protein. We are the largest collector of open reading frame clones in the whole world. We have about now 18,000 genetic loci covered, and we have acquired a company called Blue Heron, which we know how to synthesize 1 million base pairs. What's relevant here is, in order to develop assays for every single human protein, you literally have to purify every single protein. So we have now already produced 15,000 transfected antigen. I will elaborate a little bit more later. But we have already now purified 6,000 human full-length protein from mammalian cell HEC293 cells. So this is actually one of the reasons we can actually do high throughput antibody production. And we have about 30,000 cases of cancer patients. We can even track outcome data for patients. We actually have a very broad Luminex license from Luminex, eventually our long-term goal is to put all these antibodies on pairs so we can eventually do multiplex pair. But today I will share with you our antibody production and the 10K chip. So the question is, how do you develop a perfect IHC antibody? So what is a perfect IHC antibody? So in the IHC area, in the end, quality is everything. If you don't have quality, don't even bother to make an antibody. Because if you have a dirty antibody, you might as well not make one. Okay, so that's our philosophy. So if we don't have the right tool to assay the antibody, we don't even want to make it. So it turned out to be that now we have a pretty good toolbox. One of the toolbox is we can actually use our lysate as an antigen standard. Because when we transfect a full-length cDNA clone into HEC293 cell, because this clone has a tag on it, we can quantitate how much antigen is in each, we can literally do a titration of our antigen and immediately know which vendor's P53 antibody is the most sensitive antibody. Because this actual vendor has the best, most sensitive P53 antibody, but some of the antibodies are pretty bad. This antibody has, is not very sensitive, can't detect 2 nanograms of P53, but even when they can detect it, they see multiple bands of P53. So even on detection side, there's tremendous amount of variability in the marketplace. But on the specificity side, it's even more challenging. So, because if you think about IHC application, I actually think IHC application is the most challenging application. Because if you think about a antibody pair, because you're using 2 independent antibody, so your likelihood of getting specificity is higher. Because if you made a rabbit antibody, a mouse antibody, the likelihood of those 2 antibodies will hybridize against the same noise is low. But IHC, you're using 1 antibody, and your tissue is full of human protein. Especially you're trying to detect cancer tissue. Every single cancer tissue, the gene expression level is different. So you have even more a daunting challenge. So to me, actually, an IHC antibody specificity has to be the #1 criteria of, for a antibody. It's like going to fish, to do a dirty pond to try to catch a particular fish. Your fish hook better be extremely specific. Otherwise, you're going to pull out all kinds of stuff. And then you're going to write a pathology report to the patients and tell them what to do. And that is to me, it's very nervous if I'm that. So we think actually this antibody here gotta be the most specific probe on Earth. And so how do we do that? And this is actually what we'd like to share with you. This, after all these years, 16 years worth of work, we have now produced a antigen chip. Okay, so we basically take our 16-year worth of work, we took all our open reading frame clones, we transfect them into HEC293 cells. So this is tens and thousands of transfection, okay? And then we validate every single one of them by doing Western blot. Because all these clones has a tag on it. It has a MIC and flag tag. So we can know this gene has been expressed. Okay, then we can do different extraction. We can do it. And then we, in this particular case, we take the whole lysate. We don't purify the protein, okay? Because a lot of membrane protein, like GPCR, the word, is very difficult to purify. Actually, in the context of the lysate, it's pretty easy to isolate. So then you just spot. Each dot is basically an overexpressed lysate antigen, okay? So this chip has 10,000 human antigens on it. It's about half of the whole human proteome. Okay, so now with this tool, finally, when you have an antibody, you can say, well, I can check entire half of the whole proteome to see whether they're specific or not. Okay, that's the message. And eventually, we would like to have the entire human proteome on it. I think this end of this year, we are planning to print a 15K chip. So we finally now have already produced 15,000 lysate. So we can produce a 15K chip. So this is actually the lysate chip, 10K chip printed. And so we're using this mainly to assay antibody specificity. And so any antibody can pass our 10K chip specificity. Now we are calling these antibody UltraMab. Stands for ultra specific, basically. Okay, so one of the investment we made in the last 3 years is to build a large-scale antibody production facility in China, because antibody production, unfortunately, is extremely labor-intensive. It's a numbers game. If you want to have a good, high-quality antibody, the best thing to do is to have lots of hybridoma to pick from. So we basically using high throughput, and we do a vigorous testing. But for UltraMab, really there's two criteria for UltraMab. One is that they have to pass our microarray specificity test. And we have, the pathologist we use has to like the sensitivity of our antibody. That's the two main criteria. And I'll share with you a few examples why UltraMab is so important. So this is actually a case we did with an antibody called ERCC1. And I think in this audience, everybody probably know what ERCC1 is. It's basically, it's one of the DNA repair enzyme. So if ERCC1, the thesis is if ERCC1 is overexpressed, when cisplatin is used, and creates the damage to the DNA, the tumor cell knows how to repair it very quickly. So therefore, the tumor cell is resistant to cisplatin treatment. So if the patient has high level of ERCC1, they are not good candidate for cisplatin treatment. Okay, that's what I understand. Okay, so this is the New England Journal of Medicine paper looking at ERCC1 negative tumor. With drug treatment, without treatment, there's definitely a difference. But if the tumor is positive, it's less of a difference. I think that's the thesis. I heard some people don't believe this, but this is at least the New England Journal of Medicine paper. So this is not my job to convince you whether ERCC1 is a marker today, but I'll convince you that the ERCC1 used to publish New England Journal of Medicine is not a good antibody. So there's actually a group in University of Pennsylvania basically first published a paper saying that that antibody is not specific. So this is a cell line. They actually knocked out ERCC1. So if they knocked out ERCC1, technically you shouldn't see any signal from ERCC1 antibody, but they still see a band. It's about the same size from this clone called 8F1. Okay, so so what is this band? They obviously don't know. Actually, as a matter of fact, if you read the criticism of that paper by the French group, is that they should do mass spec on this band to find out if they are. But doing mass spec is not that easy. Okay, so what we did is we immediately took this antibody and hybridized with our 10K chip. And of course, unfortunately, this is hard to read, but of course, this antibody binds to ERCC1. But it binds to another gene called a PCY-T1A. I don't even know what that gene is, so obviously. So it's a very strong signal, okay? So if you actually run a Western, and it's clearly this hybridoma, ERCC1, not only binds to ERCC1, but it also binds to this protein called a PCY-T1A. So without the protein chip, it will take forever to find out what it binds to. But this takes us 1 day. We can actually find out what it binds to. And because we already, usually by the time you see a signal, we already have the lysate, right? So we just run a Western blot to validate it. So this antibody, this hybridoma, pathologists are using, indeed, at least on our chip, binds to 2 antigens, okay, ERCC1 and a gene called PCY-T1A, okay? So, and another paper even recommended a Rabbit Polyclonal antibody called FL297. On our chip, this antibody is even worse, okay? It binds to at least 3 different proteins. It binds to a protein called PDPK1. It binds to another protein called FERMT3. And of course, it binds to ERCC1. So the question is, when you have these dirty probes, how much confusion is creating in the field? Okay, so this is actually just to show you, this is a Rabbit Polyclonal antibody. It cross-reacts with this protein called FERMT1. So it turned out to be this cross-reacting element is actually a nuclear membrane protein, and ERCC1 is a nuclear protein. So we think it should interfere with the signal. Okay, so so this is actually an antibody against PCTY1, and you can see it has similar pattern. My understanding, I'm not a pathologist. Okay, so if I'm making false statement, correct me. Okay, this is PCY-T1A, and this is 8F1. And apparently they have the same nuclear localization. So pathologists always like to say, okay, if P53 is supposed to be in the nucleus and I see nucleus standing, the antibody may be good. Okay, so to me that's not good, because at least when we do Western blot, we separate the protein pretty far apart. But when you look at the cellular compartment, every compartment still have thousands of protein in it, okay? So doesn't really, be in the right location is really by no means it's the right antigen. Okay, so here's an example. So if you do qPCR, we want to find out, okay, so let's say this protein will be detected by 8F1, a commonly used antibody by pathologists. Would that create problem for cancer? So we just look at cancer patients. It turned out to be some of the cancer patients express a lot more PCY-T1 than actually ERCC1. See, look at this patient. The ERCC1 level is very low, but the PCY-T1A is extremely high. So for this particular patient, whatever the ERCC1 positive pathology is writing, I think it's mostly probably coming from the signal from PCY-T1, not from ERCC1. So we think this is probably one of the biggest challenge of IHC antibody, because if you don't know how clean that antibody is, and because cancer is so heterogeneous, how do you know that particular patient didn't overexpress another gene, in this case, that actually is the contaminant you are detecting? Okay, so that's why we think the UltraMab we think it's important enough. That's why we decide to dedicate tremendous amount of energy in this area. So we decided to try our strategy to make the most specific antibody for ERCC1. So and we went ahead and immunized huge number of animals. We eventually got 12 IF positive, 9 IHC positive antibody, and we had got 15 flow positive antibody. But out of all these antibody, only 2 antibody actually can pass the test of being specific on our 10K chip, and then the pathologist likes the reading, okay? And it turned out to be there's only one antibody is called 4F9, and another antibody is, so this is actually the 4F9 protein chip. It's very specific. We couldn't see any, because each dot you can digitalize it. So you can actually have a real reading for each dot. So you can definitely, you can't miss it when you see a contaminant showing up on our 10K chip, okay? So, and this is our 4F9. We call this one will be an UltraMab. And it clearly don't cross-react with this gene PCYT1A, like 8F1. And this is the 2 hybridoma we have. One is called 4F9, one is called 2E12, and passed our UltraMab. And luckily, this one now is already been licensed, one of the large antibody, pathology company. So these are actually now slowly coming to the market through different channels. We actually, since we have, our ZS Bio channel in China, so the Chinese pathologists are already using these antibody. So I always challenge the US colleagues and say, if the Chinese can actually use better quality antibody, I think you need to do the same for the American patients too, or Canadian patients too. Because we should never use dirty antibodies for our patients, okay? So ERBB2, we actually have done quite a few antibody. We actually picked out a few to showcase to you that what we actually realize, I'm making a very provocative statement. We actually find about 50% of IHC antibody are not specific. 50, more than 50 actually. So here's, we show these data not to make other people mad, because we really just want to share it with the field that, with this new innovative technology, we finally has a test for specificity, okay? So here is the commonly used FDA-approved 4B5 monoclonal antibody for HER2, okay? And when you look at our chip, it binds to 3 genes. It clearly binds to HER2, it binds to HER4, and it binds to another gene called ZSCAN18. And this is FDA approved, okay? And it can be easily validated by Western blot. And this clone 4B5 binds to HER2, HER4, and ZSCA18. We actually think that this is why, because HER4 is highly expressed in some of the gastric cancer patients. So if you have an antibody binds to both HER2 and HER4, if one patient has extremely high HER4, you're going to give them a HER2 3+ reading at IHC, okay? So that's why some of the IHC data don't correlate with fish data. Because at the protein level, you're really seeing these 3 proteins, right? But at the DNA level, you're not seeing all these three gene amplified. So this is actually just showing you that, specificity is such an important criteria in the IHC area. And this is actually a polyclonal antibody, because there's actually a group of people, this polyclonal again binds to multiple targets, at least 3 in this case. This is already considered to be a very, very high quality polyclone. It's affinity purified and everything. And it still binds to 3 targets. In the whole human protein. I'm actually hoping that by the time we made another 10K chip, we don't find even our UltraMab are seeing some strange targets. I hope that's not the case, okay? So, but 10K chip is the best we have right now. And so we actually now have a HER2 candidate, which is very specific, but unfortunately we don't even know if the pathologists like this antibody yet. It's being tested right now. We're hoping this antibody will be loved by the pathologist. Okay, so this will be our HER2 test. Okay, so the UltraMab. So I think in summary, we basically looked at the antibody on the market, and significant number of IHC antibodies are not specific when you are testing them against 10,000 antigens. Okay, we have developed a toolbox, which is basically a 10K, half of the whole human proteome antigen chip. Now we can use this chip to kind of at least have, to have the first check how specific the antibody is. And so we are now committed to launch a whole new set of antibody for the IHC market. Basically, they have to pass the 10,000 antigen standard, and it has to meet the pathology's sensitivity test. And right now, we already released about 10 UltraMab, and this year, our goal is to release about 100 of them, because it's actually a lot of work to get one UltraMab right, because we actually, even some of our monoclonal antibodies, we thought it was pretty good, but the moment you look at 10K chip, they bind to 4 or 5 antigens. So monoclonal antibody, by definition, people think monoclonal antibodies are monospecific. It turned out to be 80% of monoclonal antibody are not monospecific. Okay, so you need to do a lot of selection to find that 10% of the antibody which truly are monospecific. Okay, so we actually use full-length protein to do immunization. So we have a pretty wide spectrum to pick the right epitope. If you just use a peptide, I actually think one of the problem of these HER2 antibodies is they are made by a peptide antibody. So because they have a you force the animal to only react to that epitope. Okay, so you don't have much choice. When you use full-length protein, you at least have a much bigger library to pick from. That's our theory is, okay? So we're very much interested in working with everybody to eventually at least upgrade all the primary antibody to these very, very specific antibody. We are very committed to launch a 15,000 antigen chip by end of this year, so most of the antibody will be checked against two-thirds of human proteome. You know, we think about if after we can check two-thirds of whole human proteome, if that antibody doesn't bind anything beyond two-thirds of the proteome, that antibody might be pretty specific. Now, actually, let me share with you. Actually, the chip we developed, most of the drug target was preferentially selected. So we always work on the so-called druggable genome first. GPCR, ion channel, tyrosine kinase receptor. So that 10K chip has most of the druggable targets in there. So in the sense, this chip is already pretty good when it comes to develop a pharmaceutical. It's not necessarily the most comprehensive human proteome tool, but for drug target, it's already pretty good because we always clone the drug target first, GPCR, ion channel, the word. So this is, our effort to, to contribute to this field, and we really are looking forward to work with everyone. So if we show some of your antibody, some of the antibody is not specific, it's not personal, we're not trying to make anybody look bad. We just really want to say, maybe the cancer patient do deserve a better HER2 antibody. Okay, so, and we hope that we can all work together to provide the patient with the most specific antibody on Earth. Thank you very much.